Hello friends, welcome back to NPTEL online certification course on soil and water conservation engineering. I am Rajendra Singh, professor in agriculture and food engineering department of IIT Kharagpur. We are in week 6, lecture 30, and the topic is basics of open channel hydraulics part 2. To give you an overlook of what we have covered in this week up till now, we started this week with lecture 26, where we introduced gully control measures. In lecture 27, we focused on gully control measures with respect to permanent structures. Lecture 28, we dealt with design considerations for permanent gully control structures. In lecture 29, we went through the basics of open channel hydraulics part 1, and today's lecture is continuation of that, that is basics of open channel hydraulics part 2. Last time we discussed the concept of specific energy, and today we continue with the application of specific energy concept, especially with reference to flow over a raised hump. So, the case is, suppose there is channel where there is a raised hump, suddenly a raised hump comes. This is the concept I also mentioned, is used in broadcasted weirs also. So, if upstream depth and discharge are known, that is at this any point upstream, which is point 1 here, if depth and discharge are known, then specific energy concept can be used to find the velocity and depth over the hump. So, velocity and depth over the hump can be found out by knowing the upstream conditions, and that is because of the application of specific energy concept. So, if we apply Bernoulli's energy equation over section 1 and 2, section 1 you to notice is at the hump, where the hump height is delta z. Assuming horizontal rectangular channel, that is z 1 equal to z 2 and taking alpha equals to 1, that is in Bernoulli's energy equation. So, we get y 1 square y 1 plus v 1 square by 2 g equal to y 2 plus v 1 square v 2 square by 2 g plus delta z. So, basically here, so elevation head is not there. So, it is the pressure head and velocity head, that is there, and of course, this z is inbuilt part of the depth of flow, because depth of flow is lesser here due to this hump. So, this is equation number 14. We are continuing with the equation number, earlier equation number. So, in terms of specific energy, because we know that specific energy is nothing but y 1 plus y plus v square by 2 g. So, that means equation 14 can be written as y 1 E 1 equal to E 2 plus delta z, that is equation number 15. So, point A on specific energy curve corresponds to section 1. So, section 1 where the depth is very high, and if you go here, this is the point on specific energy curve. If we draw for this flow, then this is specific energy for this point A corresponds to the flow depth on the upstream side. However, as seen, point B or B dash may represent section 2. So, both these 2 points have because here you see the energy, here the depth is z and energy here is E 1, wherein this is E 2, that there is a difference of delta z from this equation. So, E 1 is E 2 plus delta z. So, this is E 2 plus delta z is E 1. So, that is what it is. So, this E 1 corresponds to section 1 and E 2 corresponds to section 2, but same energy E 2 is obtained at 2 points B and B dash. Then the question is, which of these two, B or B dash, represents section 2. So, obviously, we can say that point B corresponds to specific energy and flow depth at section 2, because in between section 1 2 there cannot be 2 points where E 1 minus E 2 is equal to delta z. So, because difference of these two is delta z. So, between this point and this point there cannot be another point. So, that is why this point basically represents section 2. So, point A corresponds to section 1 and point B corresponds to section 2 on the specific energy curve. So, if we take example, a rectangular channel with flat bed and width 5 meter and maximum depth 2 meter has a discharge of 10 cumecs. the normal depth is 1.25 meters. What is the depth of flow in a section in which the bed rises 0.2 meter over a distance of 1 meter? Assume that fractional losses are negligible. So, that means we have been given channel bed width is 5 meter, discharge is 10 cubics or cubic meter per second, y 1 is 1.25 meter, that is normal depth is given, and delta z, that because there is a rise, bed rise is 0.2 meters. So, delta z is 0.2 meter. So, that means we can, for a ramp case, we know that from specific energy concept E 1 equal to E 2 plus delta z. So, we also know that E equals to y plus v square by 2 g. So, that means for E 1 section 1 we can write E 1 equals to y 1 plus v 1 square by 2 g, or y 1 we can replace v by q by a. So, y 1 plus q square plus divided by 2 g a 1 square, and we know the value of y 1, we know the value of discharge q, and cross sectional area, because we know the bed width, we know the depth of flow. So, cross sectional area b y we can find out, and value of g is also known. So, everything is known here. So, by putting the values we get E 1 equals to 1.38 meters. Similarly, specific energy at section 2, assuming depth of flow y 2, we can write in terms of y 2, E 2 is y 2 plus q square by 2 g a y 2 square, or y 2 plus 10 square, that is because q equals to 10, to 9.81 5 y 2 square. That means, if we simplify, we get y 2 plus 0.2 by y 2 square, and we know that E 2 equals to E 1 minus delta z from previous equation, and so y 2 plus 0.2 y 2 square, which is here, is equal to 1.38, that is E 1 value we have already obtained, and z delta z value we already know is 0.2. So, from here y 2 plus 0.2 by y 2 square is 1.18, and because y 2 is only unknown. So, we can solve by trial and error, and we get a value of y 2 equals to 0.96 meters. So, this shows that the water level at section 2 is 1.16, that is 0.2 from the bed if we bed elevation. So, 0.2, which is a jump ramp height, plus 0.96, that is 1.16 meters, and there is a drop of 9 centimeter in water level due to 20 centimeter rise in the bed, because the upstream flow depth is 1.25 meters to 1.25 meters, wherein the depth at the ramp is, including the ramp height, comes out to be 1.16 meters. So, there is a drop of 9 centimeters in water level due to 20 centimeter rise in bed. So, that is the one of the concepts of specific energy, because using a specific energy we can find out the flow depth at the ramp. Then we come to hydraulic jump, that is hydraulic jump is defined as a rise in the level of water in an open channel. So, if water level rises suddenly, then this phenomenon is referred to as hydraulic jump, and it occurs when water flowing at a high velocity is retarded to a slow velocity. Suddenly, if flow is supercritical, that is flowing at a very high velocity, then if it is retarded because of certain region, then obviously there will be a sudden rise in the level of water, and that is referred to as hydraulic jump. And the slowing of water leads to an increase in height that changes the kinetic energy of flow into potential energy, and in the process some of the energy dissipated in the form of heat due to turbulence. So, basically the hydraulic jump phenomena is used for energy dissipation and often designed to occur over dam spillways. So, on the downstream side of the dam spillway, where the water flows with a very high velocity, then we create a condition such that hydraulic jump occurs and energy is dissipated, so that the downstream channel remains safe. Also below the sluice gates in the channel. So, if the sluice gate is there, then also because of the flow conditions changing drastically, there will be hydraulic jump formation. and also occurs when channel slope changes from steep to mild. So, whenever there is a flow condition changes that from supercritical to subcritical, then we have the hydraulic jump phenomena taking place. So, if we try to analyze hydraulic jump, since hydraulic jump involves large energy losses, energy or specific energy equation cannot be applied, because we saw that energy remains more or less constant in the specific energy. Previous equations we saw, we neglected the losses, or there are minor losses because of the friction. But because hydraulic jump phenomena, lot of energy loss is there. So, that is why we have to apply momentum equation in this case. So, that means if we consider a control volume containing the hydraulic jump here, then we have to consider the forces acting on this control volume. So, if we consider that, then obviously because of velocity of flow there is a force acting in the flow direction, flow is taking in this direction, and then hydraulic jump phenomena occurs. So, that means there is some retardation, and then a flow force is created which acts in the opposite direction. So, resultant force in x direction will be F 1 minus F 2, and momentum change will be obviously m 2. If you consider momentum here m 1 and it is m 2. So, the momentum change m 2 minus m 1, and as per this momentum equation, the momentum change equal to total change in the forces. So, from this we can write F 1 minus F 2 is equal to m 2 minus m 1. Or we can rearrange and write F 1 plus m 1 equal to F 2 plus m 2 is constant. And if you consider a rectangular channel, then F 1, that is force at section 1, is pressure times area, and pressure is basically rho g h. So, rho g h basically if it is a rectangular section, then force acts at the center. So, center of the depth. So, that is why y 1 if y 1 is depth, then y 1 by 2 that will be centroid. So, rho g y 1 by y 2, and the rectangular channel. So, y 1 times b is the y 1 times b is the depth of the cross sectional area. Similarly, if you consider momentum at section 1, then momentum is mass into velocity, and mass is nothing but rho times q, and velocity is v 1. So, again velocity we can write in terms of q and cross sectional area. So, q and cross sectional area. So, b y 1. So, this is what it is. So, similarly, if we can write F 2 equal to rho g y 2 by 2 y 2 b, and m 2, this will be m 2. So, m 2 is rho q q by y 2 b. So, we are now writing everything in terms of q and y. And if we equate that and we rearrange the terms with little bit of manipulation, we get this formula which says that y t equals to y 1 by 2 bracket square root of 8 plus f r 1 square minus 1. And important thing is that here f r is Froude number. We remember the earlier we used f for Froude number, but because here in momentum equation f is being used to represent force. So, if that is why we are writing f r. So, f r 1 is Froude number at section 1, basically it means that Froude number at section 1. So, y 1 and y 2 are conjugate depths. So, using this relationship we can find out, knowing if we know the Froude number, that means the velocity of flow and the depth of flow or discharge in the upstream section, then we can find out the conjugate depth in the hydraulic jump. Similarly, if we manipulate this equation little bit, then the energy loss in the hydraulic jump can be obtained in the form of this relationship, that is delta is y 2 minus y 1 cube by 4 y 1 y 2. So, if we know the conjugate depth, we can find out how much energy loss is taking place in a hydraulic jump phenomena. And also based on experiments, the length of hydraulic jump, that is distance which is measured from the front face of the jump to point on the surface immediately after the roller. So, basically here from here to this is the place. So, this is nothing but this is the length of the hydraulic jump, and this length is experimentally determined at 6 y 2, and that is true only when f, that is Froude number, remains between 4 and 20. So, if Froude number is 4 and 20, the experiments showed that within this range length of the hydraulic jump was 6 times y 2. So, if we know the y 2, we can also find out what is the length of the hydraulic jump. So, we now come to practical applications of hydraulic jump phenomena. Hydraulic jump is used in design of stilling basins for energy dissipation, and as we know, stilling basins are used as a terminal structure in a spillway. So, many times we have talked about apron, basically this apron, and this stilling basin is also acts as a apron in a structure. So, stilling basins are used as terminal structure, that is a last structure. So, the flow falls on this apron, and it is expected that hydraulic jump phenomena will occur and energy dissipation will take place. So, stilling basins are designed in such a way that hydraulic jump is created, so that high level of kinetic energy is reduced through dissipation and by a transfer to potential energy due to greater subcritical flow depth. So, we know that in the hydraulic jump phenomena the flow depth rises. So, obviously, the kinetic energy gets converted into potential energy, and also because of the roller formation and so on, lot of energy is further dissipated. So, this helps in controlling scour and erosion of the downstream channel, because if a very high velocity flow will go into the downstream channel, then that might cause erosion, because you remember every time when we design gross waterway, we always talked about the non-erosive velocity. So, we always want to focus on non-erosive velocity, or we want to have control velocity, so that erosion can be minimized, and that is what happens here, that when hydraulic jump phenomena occurs, we do not want very high flow velocity to go into the downstream channel, and that is why we see that we put prints or stilling basin, so that hydraulic jump phenomena occurs, the kinetic energy gets converted into potential energy, and because of this conversion process lot of energy loss takes place and the velocity of flow gets reduced, so that downstream section of the channel remains safe from scour or erosion. Flow at the lower end of a spillway of a dam is usually supercritical. Since flow in the channel downstream is usually subcritical, hydraulic jump forms near the base of a spillway. So, this is what we are talking about, because very high flow, and because we are seeing that the velocity is retarded. So, there will be a rise in the water level, and that is why in between hydraulic jump phenomena will take place. Now, the downstream portion of the spillway must be designed so that hydraulic jump always forms on the concrete structure itself. So, the concrete apron which we provide here, that is here, the hydraulic jump phenomena must occur within the confines of this apron. If hydraulic jump forms downstream of the concrete structure, say for example, instead of in figure A, it is happening here, but if it forms beyond this apron, then severe erosion of foundation material could undermine the dam and cause complete failure of it. So, that is also a very important design consideration, that when we design apron or stilling basin, we must always see that hydraulic jump phenomena does occur over the apron or the concrete structure itself. And US Bureau of Reclamation have standardized the stilling basin designs, and this we will see when we discuss later on when we go into design of chute spillway in a greater way. We will see all these design of stilling bases and all little later, maybe later in the course. So, let us take one example. A hydraulic jump occurs downstream from a 15 meter wide sluice gate. The upstream depth is 1.5 meters and the velocity is 20 meter per second. Determine the Froude number and the Froude number corresponding to the conjugate depth, and the depth and velocity after the jump and the energy loss in the jump. So, all these we have to find out. So, we have been given the data given are velocity, upstream velocity is 20 meter per second here, and upstream depth, that is y 1 equal to 1.5 meters. So, Froude number for upstream section F 1 is V 1 by root g y 1, that is a standard equation. We know V 1, we know g, we know y 1. So, by putting the value we get the Froude number is 5.2, and this is greater than 1. So, the flow is supercritical, that is very important to notice. And once we know y 1, then and we know the y 1 and we know the Froude number, then we know the equation to find out the conjugate depth, that is y 2 equals to y 1 by 2 square root 1 plus 8 f r 1 square minus 1. So, we know f r, that is Froude number, upstream Froude number, which is here, and y 1, that is depth of flow we know. So, by putting the known values here, we calculate y 2 comes out to be 10.3 meters. So, that means the depth of flow goes up from 1.5 meters to 10.3 meters in the hydraulic jump phenomena. And then of course, from continuity equation we can calculate V 2. So, it is V 2 is A 1 B 1 A 2 B 2. So, 1.5 times 20 and then divided by 10 by 3. So, we get 2.9 meters per second, that is the velocity of flow, and downstream Froude number then can be found out V 2 by root g y 2. So, V 2 is known, g is known, y 2 is known. So, we can put the value as 0.29, and using the equation, the energy loss can also be find out. This is a standard equation, y 2 minus y 1 cube 4 y 1 y 2, y 2 is known, y 1 is known. So, by putting the value we can find out, and delta E comes out to be 11 meters. The flow depth goes up from 1.5 meters 10.3 meters, and there is a energy loss of 11 meters in the hydraulic jump phenomena. So, that is what we get from this problem. Another example we can take: water on a horizontal apron of 30 meter wide spillway has a depth of 0.2 meters and a velocity of 5.5 meter per second. Determine the flow depth after the jump, the Froude number before and after the jump, and power dissipated within the jump. So, V 1 is given, y 1 is given. So, here also at section 1 Froude number can be found out, V 1 by square root of g y 1. Putting the values we get f 1 equal to 3.9, and then using the standard equation we can find out conjugate depth, where y 2 equals to y 1 by 2 square root of 8 plus 1 plus 8 f r 1 square minus 1, y 1 is 0.2, f value we have obtained is 3.9. So, by putting these values we get y 2 equals to 1 meter. So, here flow depth goes up from 0.2 to 1 meters. And continuity again here. So, here we can find out A 1 V 1 A 2 V 2, and from here we can find out that it comes out to be 1.1 meter per second. So, downstream Froude number will be F 2, that is V 2 by square root of g y 2. So, V 2 is known, y 2 is known. So, this value comes out to be 0.35. So, it is a subcritical flow less than 1, and energy loss equation we know y 2 minus y 1 cube 4 y 1 y 2. So, these values are y 2 y 1 is known. So, we can put the value and we get a energy loss of 0.64 meters. What we have to find is power dissipated, and power dissipated we know is gamma q h. Gamma value we know is 1000 kg per cubic meter. Q is area times velocity. So, we can find out here, and h is we have found out, that is the total energy loss. So, from here we get it is 21,120 kg meter per second, that is the total power dissipated. Energy loss was 0.64 meters and power dissipated 21,120 kg meter per second in the hydraulic jump phenomena. So, this is how we can design how much energy is getting dissipated or how much power is getting dissipated and so on in the hydraulic jump phenomena. So, now we come to gradually varied flow. So, in a rapidly varied flow hydraulic jump phenomena, because there the flow depth changes over a very short distance, and that is how we distinguished rapidly varied flow and gradually varied flow. It was assumed that the friction losses are insignificant, reasonable because rapidly varied flow occurs over a short distance. But since gradually varied flow occurs over a long distance, friction losses are considered. So, that is the major difference here. Rapidly varied flow occurs over a very short distance. So, friction losses are negligible, where in gradually varied flow, because flow that or rather depth etcetera changes over a long distance. So, friction losses are considered. And specific energy curve shows that for a given Q there are two flow depths that are possible in a steady flow, and from Manning's equation all the time we have found one depth, and that depth is referred to as normal depth. So, the consideration of channel slope and friction helps us in deciding whether this flow is subcritical or supercritical. So, we have to calculate the normal depth using Manning's equation, and we have to calculate the critical depth using equation we have already seen critical depth formula. So, critical depth we can calculate. So, y 1 may be greater, less than or equal to y c. So, this two depths we have calculated y n, and second depth is y c. So, first is calculated by Manning's equation, second is the critical depth by using standard formula, and then we have two depths. So, then these two values y 1 may be greater, less than or equal to y c, which is quite obvious. And if that is so, then for a given channel and roughness, if y 1 is equal to y c, that is possible only if the slope of the channel is critical, because only at critical depth, because critical depth is only 1, and so normal depth will be equal to critical depth only if the slope of the channel is critical. So, this is one finding. Second is, if slope is less than critical slope, that is here, and y 1 is greater than y c, that is normal flow depth is greater than critical flow depth, that is this is the normal flow depth. So, this is y c, this is here it is here if it is y n, and then obviously we can calculate the critical depth for any given flow condition. So, flow will be subcritical and slope will be called mild. So, if S g is S 0, that is bed slope is less than critical slope, and y n, that is normal depth, is greater than critical depth, then the flow will be subcritical, that is here, and the slope will be mild. On the other hand, if slope is greater than S c, that is here, and y n is less than y c. So, here you see y c is line is up, dashed line, whereas y n has come down. So, this is y n. So, this is y c, y n. So, y n is less than y c, then flow will be supercritical and slope will be steep. So, from mild to steep slope if we go, flow changes from subcritical to supercritical. On the other hand, it is just reverse, that is from steep to mild slope if you go, then also flow changes from supercritical to subcritical, and in this case hydraulic jump phenomena takes place. So, these are the changes. And considering the energy equation 2 of lecture 29, that very common equation, that is y 1 plus v 1 square by 2 g h 0 delta x and y 2 plus v 2 square. So, for a reach of delta x in length, defining S f h friction slope, that is h l by delta x. So, only change in this equation is in place of S l h l we are writing S f delta x in terms of friction slope S f. So, this is equation number 19, and if we say delta y is equal to y 2 minus y 1 and v 2 square by 2 g minus v 1 square by 2 g is d by dx v square by 2 g delta x, and if we put this in the equation number 19, then we get y 2 minus 1 that we are bringing on this side. So, this is becoming delta y. This S 0 minus S f also we are bringing on this side. So, S 0 minus delta x, S f minus delta x coming on this side, wherein this v 1 square by 2 g we are taking on this side. So, it becomes v 2 square minus this thing, and then we can write this term here. So, it is d by dx v square by 2 g delta x, equation number 22. So, simple manipulations of the terms on left and right hand side. So, dividing the entire equation by delta x and taking the limit as delta x approaches 0, we get dy by dx plus d by dx v square by 2 g is equal to S 0 minus S f. And second term can be rewritten as d by dy v square by 2 g times dy by dx. So, from here dy by dx, and that is dy by dx and dy by dx we can take common, and then we can write for dy by dx, it is dy by dx will be S 0 minus S f 1 plus d by dy b square by 2 g. So, we are just manipulating this term little bit, instead of writing d by dx we are writing d by dy and then dy by dx. So, that basically it means the same, but then it helps us in finding out dy by dx a single term. Now, this equation dy by dx is simply tells what? Depth, change in depth with x. So, that means it tells us the water surface profile, how the depth changes with distance, basically this equation. But this equation can be converted into more usual form if denominator is expressed in terms of Froude number, and that is why we do little bit of manipulation, and then finally, we can write this equation as dy by dx equals to S 0 minus S f divided by 1 minus f r square, f r is Froude number. So, now we have dy by dx in terms of S 0, S f and Froude number, and this is a general differential equation for gradually varied flow, and this is used to describe the various types of water spray profiles that occur in open channel. So, using this one can find out the water surface profiles. So, if we take an example, water flows in a river shown in figure with a uniform bottom slope. So, slope is bottom, slope is uniform. Total depth at each section is measured by using Pettit tube as indicated. So, here in the center of the channel and at certain height, and here center of the channel certain height, total head is measured. Value, determine the value of dy by dx at a location where the Froude number is 2.75. So, these are the values which are given to us, and the distance between two sections is 1250 meters, that is also given to us. So, this equation dy by dx is S 0 minus f 1 by f r square. So, we know that y 1 plus v 1 square by 2 g equal plus S 0 S x, this is the basic equation we are writing, or from here S 0 minus S f is 1 by delta x y 1 plus v 1 square by 2 g minus y 2 plus v 2 square by 2 g. We are doing it because these values are already available from Pettit tube measurement, and delta x is also known. So, that is why we can calculate S 0 minus S f directly. So, by putting the values delta x 1250, y 1 v 1 square by 2 g value is given, difference is 191.5 minus 189 for this section, and for second section this comes out to be 2 meters. So, S 0 by S f is 1 by 1250 and 2.5 minus 2, that means 0.0004. Putting the value of S 0 S f and f r in 2.75, that is where we have to find out the profile depth. So, dy by dx comes out to be 0.0004 divided by 1 minus 2.75 square, or we get a value of minus 6 into 10 to the power minus 5, and minus value shows that there is a fall in depth as we move towards the channel for the given condition. So, that is how we have seen now in this case first the application of the energy concept, then we went into the rapidly varied flow in the form of hydraulic jump. We saw the concept of hydraulic jump, its application, and then finally, we moved into the gradually varied flow and saw how the fundamental equation of gradually varied flow could be used for designing the water surface profiles. And all these concepts are very useful when we go into designing various permanent gully control structures, and we will see this application. So, I will expect that you will go through this part very carefully and keep some of the basics in your mind, because that will be helpful when we design the structures. Thank you very much.